All right, let's talk about plastics. I mean, they're literally everywhere. But have you ever really stopped to think about why they break down? Why they don't last forever? Well, today we're diving deep, right down to the molecular level to figure that out.
You know exactly what I'm talking about, right? You find that old rubber band in a drawer, you give it a little stretch, and poof, it just crumbles into pieces. Or what about your car's dashboard after a few years sitting in the sun? It gets all cracked and faded. Well, that's not just things getting old. Nope, there's a very specific science at play here, a process that's literally breaking these things apart from the inside out.
So there's a name for this whole process, of course. It's called polymer degradation. And look, it's way more than just something looking a bit worn out. What's actually happening is a fundamental change. The very things that make plastic strong, these super long molecular chains, are literally being broken, snapped apart. And that's why the material loses its strength, why it loses its shine, and why it eventually fails.
Okay, so what's the bad guy here? What's actually causing these bonds to break? Well, it turns out there's a whole army of things out there in the environment just constantly attacking our plastics. Let's meet the main suspects.
And wow, it is quite a list. You've got the obvious ones, right? Like heat and just plain old physical stress. But then you've got these invisible assassins, like UV light from the sun, ultrasonic waves, even things like high-energy radiation. Every single one of these is a unique weapon that can start snapping those polymer chains.
All right, let's kick things off with a case study. We'll start with probably the most common attacker of them all, heat. I mean, how can a little bit of warmth do so much damage? Let's find out. Okay, so here's the secret. Not all plastics are built the same. Not at all. You take different polymers, say polyethylene versus polystyrene, and they have different little chemical groups just kind of hanging off their main carbon backbone. And it turns out these little side pieces, which might seem insignificant, have a huge impact on how stable the whole thing is. And this chart just shows it perfectly. Take a look at polyethylene. Super simple structure, right? And its carbon-carbon bonds are the strongest on this list at 88 kilocalories per mole. Now, look over at polystyrene. See that big bulky group it has attached? That makes the whole chain way less stable. Its bond strength drops all the way down to 70. So here's the big takeaway. The more complicated and bulky those side groups are, the easier it is for heat to come in and just snap that chain apart. So that's heat. Makes sense. But what about just raw physical force? What happens when you just stretch or crush something? For that, let's jump into our second case study, rubber. Now, this is pretty cool. In the rubber industry, they actually want to break down the polymer. They do it on purpose. They'll take this really tough, hard rubber and run it through these giant rollers. The process is called mastication, which literally means chewing. And that's exactly what it does. It chews up the rubber on a molecular level to make it softer and more workable. So when that rubber is getting stretched and squeezed, the force isn't just breaking things randomly. It's smart. It goes right for the weakest links in the polymer chain. For polyisoprene, which is just the sciencey name for natural rubber, the weakest spots are the bonds that connect all the repeating units together. Those are the ones that are most likely to snap when you apply stress. But wait, here's where it gets really, really interesting. Okay, so the stress breaks the chains. Fine. But if that's all that happened, couldn't they just reconnect? Well, they could. Except there's a secret ingredient, a partner in crime, that makes sure the damage is permanent. And you won't believe what it is. It's oxygen. The very air all around us. Okay, get this. If you do that whole mastication thing in a room filled with something like pure nitrogen, an inert gas, almost nothing permanent happens. The broken chains, which are technically called free radicals, they just find each other again and link back up. But if you do the exact same thing with oxygen in the room, the oxygen molecules swarm in and immediately latch onto those broken ends. They basically put a cap on them so they can never ever rejoin. That's what makes the break permanent. It's all about the oxygen.
Okay, so we know what causes the damage now, right? We've got heat, we've got stress, we've got oxygen. But let's get even more fundamental. How does the chain itself actually snap? It turns out there are really only two ways this can go down. These two methods are called chain end degradation and random degradation. A really simple way to think about it is this. One process is like unraveling a sweater from the end, and the other is like taking scissors and cutting it right in the middle. So chain end degradation, which is also called depolymerization, is just like that loose thread on a sweater.
The damage starts right at the very tip of a polymer chain, and it just starts releasing one single piece, one monomer, at a time. Plink, plink, plink. The main chain just gets a little bit shorter, one piece at a time, from the end.
Random degradation, though, is a whole different ballgame. It's way more chaotic. This is the scissors approach. The damage happens at any random spot, right in the middle of the chain. Snip! So instead of one long chain getting a tiny bit shorter, you suddenly have 2 or 3 or a whole bunch of much smaller pieces.
And this difference has a massive impact on the material. Just like the quote says, think about the material's total molecular weight. With the chain end method, you're just losing one tiny piece at a time, so the average molecular weight goes down really, really slowly. But with random degradation, one single break in the middle creates 2 much smaller chains. That means the average molecular weight just plummets. It's a sudden, dramatic drop.
Okay, let's zoom out for a second. We've been deep in the weeds here, talking about molecular weights and weak links and how chains snap. But so what? Why does any of this actually matter in the real world?
Well, it is absolutely critical. If you understand exactly how a plastic breaks, you can engineer a new one that's way more resistant to heat or sunlight. That means more durable car parts, longer-lasting medical implants, you name it. It also lets us predict, with amazing accuracy, how long a product is going to last. And maybe the most important thing of all, if we know how to break them, we also know how to make plastics that break down on purpose. And that, well, that's a huge deal for helping manage plastic waste. And that really leaves us with a final, fascinating question to chew on. We've spent all this time talking about how things fall apart when we don't want them to, but what happens when we completely flip that idea on its head? By truly mastering the science of how things break down, maybe the next great challenge isn't about making materials that last forever. Maybe it's about designing materials that disappear perfectly, exactly when we tell them to.